In this video, we're going to talk about how you can use Sage to create a rather reusable bit of code that will enable you to easily find the explicit or closed form expressions for recurrence relations. So here we are going to take a look at an example. We're going to solve the recurrence relation given by a1 equals 1, a2 equals 0, a3 equals 1, and for n greater than 3, an equals 9an minus 1 minus 21an minus 2 plus 5an minus 3. Imagine that these are subscripts. Sage does not have subscripts, and I did not feel like writing underscore for subscripts, so my apologies there. So we're going to try to solve that recurrence. And first, what we need to do is, since we're going to be working with polynomials, I need to tell Sage, hey, I'm working with polynomials. The way that I do that is by writing r equals polynomial ring rr comma x. And that just tells it I'm writing polynomials in the variables x. And the next thing we need to do is we need to define our characteristic polynomial. So I'll erase it and then, put it back in there again. This is a third order or third degree if we look in the text here. Yeah, this is a order 3 linear recurrence. So it's going to be a cubic as our characteristic polynomial. And basically how this works is the first coefficient is always going to be 1. It's always a monic polynomial. The coefficient in front of the highest term is 1. And then the coefficients, the remaining coefficients will be in order. What's in front of an minus 1, what's in front of an minus 2, what's in front of an minus 3, except negatives. So my next coefficient will be minus 9 times x squared. And then the next coefficient will be positive 21 times x. And then the last will be minus 5. So that gives us our characteristic polynomial. And next, we're going to have Sage find the roots of the polynomial, and there's going to be 3 roots, and they do happen to be distinct in this case, which is nice. And you might know that this function roots is going to tell you what the roots are, and then it's also going to tell you their multiplicity. So what this code is basically saying is R1 is going to take the first root, that's what this 0 means, and then I'm ignoring its multiplicity. That's essentially what this 0 means. I'm looking at the number, not the multiplicity. The same for R2, we'll look at the second root, that's what this 1 means, and I'm ignoring its multiplicity. And R3 is going to be the third root, that's what this 2 means, and then I'm ignoring its multiplicity. If I had a fourth root, it might be something like R4 equals c dot roots, and then this would be a 3 instead. But otherwise very similar. And then I have this command here, which is going to print out what the roots are. I'll wait until, well, might as well compile. It's going to tell me some other stuff, but that command right here is telling me that the roots of my characteristic polynomial are going to be negative square root of 3 plus 2, square root of 3 plus 2, and 5. And the nice thing about Sage is that it does deal with exact values, so that's nice. It's going to tell me what those exact roots are. Now, instead of having to write out square root of 3, negative square root of 3, all these times, all I really need to do is save those roots into these variables R1, R2, and R3, and then I can use them however I'd like. So this first bit of code here defined my characteristic polynomial and found its roots. Once I've done that, I'm now ready to try to solve for the coefficients in my formula. And to use that, I'm going to use the solve command on a system of equations. So let me break down what I have here. First, I'm telling Sage what variables I'm going to be using, and those variables are z1, z2, and z3. If I had more variables, I might have like a z4 in there as well. You notice that they're inside these, little quote marks. That's important. It won't work if you don't put those in there, so make sure you do. And it goes before the first and after the last. I also found that if you put each individual one in quote marks, it works. But, save yourself some work, I guess. And then we set up the equation. And while this looks like a lot, it's essentially what we'd exactly expect. This first equation is saying that z1 times r1, my first coefficient times my first root, plus my second coefficient times my second root, plus my third coefficient times my third root, that needs to equal 1. And you can imagine that these all have a little power of 1 here, power of 1 here, power of 1 here. So it's saying that's basically the first equation I need to solve. So the first element of my sequence needs to match up with z1 times r1 to the first, plus z2 times r2 to the first, plus z3 times r3 to the first. The second equation is saying what happens if I look at n equals 2. Now I need z1 times r1 squared, plus z2 times r2 squared, plus z3 times r3 squared. That needs to equal the second term of my sequence, which in this case is 0. So that's what the second equation is doing. Notice these are separated by commas. And notice we have these double equal signs. And last but not least, this third one is saying that z1 times r1 to the third plus z2 times r2 to the third plus z3 times r3 to the third, that needs to equal the third element of my sequence, which in this case is 1. So I enter that into this thing that I'm calling just equation, or EQN. And then I ask Sage politely to solve that equation. And there's a lot of things in this solve, but let's take a look. So first I tell it which equation I want it to solve. It's solving EQN. I tell it what variables it might come across. It might come across Z1, Z2, and Z3. And then this last one is kind of important for us. We have solution dict equals true. And what that means is that once I return the solution, I should be able to extract the solutions easily just by indexing by Z1, Z2, and Z3, which I'll want to do coming up next. So by adding that line in there, solution dict equals true, that means that I'm going to be able to easily access those solutions. So I tell Sage to solve it, and after a little bit of grumbling, it gets around to doing it. What I have found, well, I will say this. I made sure to keep these roots relatively tame. Roots don't necessarily have to be tame. They can be quite gross. But when the roots started getting too gross, Sage started having a very difficult time actually solving these things, and my solutions got a little bit fuzzy. So I did try to keep this in a way where the answers are simple enough that Sage will give you the right thing instead of, kind of going off the deep end. So anyhow, Sage solves, hopefully correctly, and it gives you S1, S2, and S3. And basically, this 0 is just representing that there's only one set of solutions that works. So we're accessing that set of solutions. And then Z1, Z2, and Z3 represent exactly what you would think they do. It represents this is the solution, what Z1 equals, this is what Z2 equals, and this is what Z3 equals. And that tells me what the coefficients are going to be in my equation. And we're going to go ahead and print that there. You might have seen this earlier if you, read further down. But those coefficients end up being 4/3 square root of 3 plus 13/6, negative 4/3 times square root of 3 plus 13/6, and 1/15. I doubt you would have wanted to find those by hand, so we are grateful that Sage found them for us. Okay. Last but not least, we want to write a function that easily calculates the nth element of our sequence. And I'm just going to call it recurrence because, why not? And it will take in a value n, and I want the sequence to basically tell me the nth term of my recurrence relation. So what am I going to do? Well, the closed form expression is given by that first solution we found times r1 to the n, plus that second solution we found times r2 to the n, plus that third solution we found times r3 to the n. That's our general form for solutions to a linear recurrence. So we have it do that, and then this expand is just going to translate it from something with a whole bunch of square roots and stuff into nice integers. So it will hopefully do that correctly. And now that we have that function, first of all, we'll notice that this is a pretty general function. As long as all this code up here correctly calculates R1, R2, R3, S1, S2, S3, I don't need to go back into this and change those values. So that's really nice for us. And finally, you can test it out. We print out the first 15 elements Notice that I have the range from 1 to 16. This 1 is the first number that it'll plug in. I don't want it to plug in 0 because I don't really have a 0th term of this sequence. And as for the 16, remember that Sage range basically goes up to 1 less than this last number. So this will plug in everything between 1 and 15. And then I also have it print out the 100th element of the sequence. So let's go ahead and run that one more time just so you can see it. And of course, here we have the sequence 1, 0, 1. It started off on the right track. And as you keep going, we do see that 14 is in fact 9 times an minus 1 minus 21 times 0 plus 5 times an minus 3. So that worked. And then 105 is 9 times 14 plus 1 times negative 21 plus 0 times 5. And so on and so forth. This does end up tracking. And, you know, I will assume that that is the correct last number. I couldn't really tell you because I haven't calculated out all the rest of them in between, but I trust Sage. So that's how this works. And before we go, I want to just kind of talk about what you might need to change in this code. First of all, the good bordering on great news is that if you need to change the sequence, if you are changing this recurrence here, what that is going to correspond to is changing the characteristic polynomial. So if my recurrence is different, I need to change the characteristic polynomial to the correct one. Okay, and that shouldn't be terribly surprising. Different recurrences have different characteristic polynomials, so I shouldn't expect that this polynomial would work for every single recurrence. One that's a little bit trickier is the starting conditions. So this 1, 0, and 1, where did those show up? They showed up when I was setting up my system of equations. I need to change the right-hand side of these equations to account for different starting conditions. And we'll do a quick example like that. So let's say instead of this being 1, 0, 1, what if it was 1, 0, 2? Actually, we'll change it a little bit more than that. I want to leave this 0 there. Well, nah, we won't. Let's make this a 2. I kind of want to avoid negative numbers if I can. Oh, sorry. This will be a 1. This will be a 2. How about 3? There we go. 2, 1, 3. Those will be our starting places. So let's see what that gives us. I'll have 2 there. I'll have 1 here. And I'll have 3 there. And now my sequence should start with 2, 1, 3 instead. And we'll see what happens to the rest of it. Yay, I managed to not make it go negative. So let's, take a quick look that it at least did the 4th term right. Well, 3 times 9 is 27. And then I subtract 21. That brings me down to 6. And then I add 2 times 5. So that brings me up to 16, which is correct. So all I had to do to change the starting conditions was change the right-hand side of each equation. Now, we could also have we could have an order 4 polynomial, or an order 4 linear recurrence instead of an order 3. If we did that, I'm not going to go through all the details. That's going to be what I let you do in the 4th hour activity. But let me tell you kind of the gist of what you need to do. Obviously, your characteristic polynomial will need to change. You're also going to need to find one more root. So kind of just follow the pattern, add an R4 that calculates the 4th root of this polynomial. You might want to find yourself printing out another root by just, kind of following the same syntax. Note that there's commas between things that I want to print, and I also printed out some extra commas between the things. to make them nice and separated. You're going to need to add a variable. And probably the most time-consuming thing you'll have to do, and it's not even that bad, is you're going to have to go through each of these equations and add a fourth term, because it's going to be z1 times r1 plus z2 times r2 plus z3 times r3 plus z4 times r4. And you'll have to do something similar here, plus z4 times r4 squared, and then plus z4 times r4 cubed. And then the other part is, now I'm actually going to have a fourth equation that I need to use too, so I'll need to have the next equation included there as well. So you'll have 4 equations, and each of them will have 4 different terms on the left side. So you'll have to do a decent amount of work to update this equation line. That's where most of your work will come in. Of course, then you'll need to find another solution. You'll need to tell it to use another variable. You'll need to print out what that fourth solution is. You'll need to edit the recurrence relation by adding in that fourth term. But the good news is most of this follows the same patterns as what you see in everything else. It's just doing the next number up. So just to summarize, if you're doing a higher order, add a root, make sure you print all the roots, make sure you have all your variables, spend a good amount of time updating this equation line to be correct. Make sure you add a variable here, make sure you add a solution here, make sure you print everything, and then make sure that you add your new variables up here. Once you do all that, you should be good to go to calculate larger recurrences. So there you go.